Part 4. In this section, we have quite a few different tasks that we have to work through. So let's figure out first what it is exactly that the exercise asks of us to do. So firstly, we are going to create a spike train using this function, which is very similar to the firing rate function for the harmonic spike generator that we worked with above. However, note that the period is not 25 milliseconds, but it's 300 milliseconds, so it's much slower oscillation. And this is going to be our so-called true rate. So this is the real rate at which the neuron was spiking. Now, we park that for now. You can have a look at the code, but it's actually very similar to the code that was produced above. You see that it's no different except that the value 25 changes to 300. Then the next thing that we're going to do is we're going to approximate this firing rate using this simple dynamic equation. So what this dynamic equation tells us is that the approximate firing rate, once we solve the dynamic equation, always decreases unless there is a spike. And if there is a spike, we jump up by the value of 1 over tau. Now, the interesting thing comes from changing the value of tau and then observing what happens. So you can think of it like this. Because the tau is in the denominator, the lower it is, the bigger the jump the approximate firing rate experiences after a spike. And the higher it is, the lower the change. However, the tau will also affect how quickly the firing rate begins decaying again. So if it's very small, it will decay faster, but if it's very large, it will decay slower. And so the exercise asks of us to experiment with a few different values of tau between 1 and 100 milliseconds. And that's essentially the whole idea. We have a true firing rate and we want to approximate it using this dynamic equation and then experimenting with different values of tau, which is the only constant in the equation, to see which best approximates the true firing rate. I will just mention that we are dealing with another ordinary differential equation, and I think the best way to solve it is to separate the variables. So the constant tau with the r approx on the left hand side and the time on the right hand side. I didn't write out the full steps because it's quite similar to the solution given above, but this is the final product, which is also quite similar to what we obtained above, wherein the this term is responsible for the constant decay or exponential relaxation towards the steady state value, which in this case is 0. Now, for the purposes of this exercise, I used 4 different values of tau starting at 10 milliseconds and ending at 100 milliseconds. So we're just going to go through very quickly the code in terms of what it does. So I have a single for loop here, which actually incorporates the true firing rate generated from the Poisson generator using the harmonic function with a period of 300 milliseconds. Now, I do that in one for loop because I think it's just a little bit more efficient, and in the different for loop here, I loop through the different taus and I generate the different r approx values. So that is just given simply by the equation, except at the beginning where we need to assign a starting point. Now the exercise doesn't make it explicit what the starting point should be, so what I decided to do is to just start off with the value generated from the harmonic oscillator at the beginning, so that we have sort of like the same starting point. And then we would use the actual equation, and otherwise, if there was a spike generated on the previous trial, then on the subsequent trial, you would increase the approximated firing rate using this 1 over the approximate tau formula. And then afterwards, this is actually all done. We have finished the data collection, so to speak, and all that remains is to plot what this looks like. So in purple, you can see the real firing rate. So this was the true firing rate, which was generated by the harmonic oscillator. And then we have 4 different lines for the different taus used to generate the spikes. Now, you can see there are like clear differences popping up immediately. So the largest tau is red. And as I mentioned earlier, the larger the tau, the smaller the increase after a spike, but also the longer it takes for the exponential relaxation to make the firing rate decay towards the steady state, that being 0 in this case. However, when you have a low tau value like 0.01, in this case, the jumps are really abrupt after a single spike, but it comes down very quickly. So there's a lot more fluctuation, so to speak. Now, I know the exercise suggests to use taus from the range of 1 to 100 milliseconds, but frankly, I think this is there just to trip you up, because if you try that, the resulting graph looks terrible and is clearly not capturing very well the real behavior, since the firing rate goes all the way to the moon and back. So I think starting at 10 milliseconds is a little bit more reasonable. Now, the next thing to do is to do some mathematics on the question of which tau is best suited for approximating the firing rate from the harmonic Poisson spike generator. Now, the exercise suggests to use the average squared error of the estimate. So this is the formula for it. And essentially what we do is we just take the difference at every time point between the real firing rate, the true firing rate, so that was the purple line, and the estimated firing rate at that point, and then square that and integrate over. Now, obviously, we are using discrete, not continuous data, so it's not really going to be integration. It's really just a sum divided by length. And this is what the code for that looks like. So here we loop over the different approximate firing rates and for the different taus, and then we generate the value which is the lowest in this case. Now we can have a look at the list of the squared errors. So if you just look at the square error term, each row is a different time point, and each column is a different tau. And then we can sum over all of these rows for each of the columns. And by doing that, we arrive at this nice table. And obviously, you can see that the smallest, although not by much, squared error is for the tau of 0.02 seconds. So that is the tau which best approximates, given the dynamic equation and the list of taus which I initially chose, the true firing rate generated from the harmonic Poisson oscillator. So to answer the question, which is explicitly to determine the best value of tau, we can conclude that it is 0.02 seconds.